Good morning everyone. This is Professor Sanjay Kumar Sharma, Head Department of Mining Engineering, and we normally teach our students rock engineering, rock design, designing of structures, rock instrumentation and numerical modeling. But today we are going to discuss primarily the earth resources and rocks as a resource of earth, rocks as a resource that is not modified but utilized. And therefore, we would be during my lecture I would be informing you about how the different types of tests are conducted, why they are conducted, what can we do after we get the results from those tests, how they are utilized as inputs to design of structures on rock, within rock, besides rock. We will concretely be able to appreciate it if I name these structures, that is there are tunnels, metros, you have mines, you have nuclear waste repositories, and you will also find that all of your civil structures, there are certain different kinds of utilizations to which caverns and underground space is being utilized globally today. You have libraries built in below ground. You have stadia also, stadiums are also built below ground these days. You have huge size granaries, you have huge petroleum storage, you have water storage, you name a utilization of current civilization, and underground space is today providing that in terms of space. That means today we have to understand the rock that surrounds the space that is created by us below ground for its stability. There lies the utilization of rock engineers or geomechanics engineers. On surface when you see it, you will find that every year we find there are issues of landslides. Landslides as a rock mechanics phenomena are nothing but slope stability issue. Earth has different type of resources and 8.5 million species of different kind are utilizing it. One of the species is Homo sapiens. We today number about 7 billion people across the world, and as time passes people are estimating the carrying capacity of the earth. With passing time again we are finding that this time period which was earlier stated for carrying capacity of the earth for 7 billion people is also reducing with each day, and primary reason behind this is our unplanned greedy exploitation of the natural resources or the resources of the earth. Geomechanics and rock mechanics and earth sciences play an important role in understanding and assessing the utilization of the resources that are found as and are utilized without modification. Rocks, soil of different kinds are utilized without much modification, and even today if you go to places like Jaisalmer, Jodhpur and even locally at Varanasi, you will find that the stone or rock, sandstones are deployed as such as building material without such modification. Now coming back to our earth resources, rocks and soils are resources found in earth which are utilized with minimum modification. You will find examples of utilization of these resources in many areas in India, particularly if you go to Jaisalmer or Jodhpur, you will find yellow sandstone is being used as building material with no alteration at all. Marbles are still being utilized without any addition or deletion on their structure as a material. Similarly, granites are being used. Back home in Varanasi, we find Chunar sandstone is used in a big way as a building material. So, we today require to understand how a rock will continue to behave in its lifetime. How much strength can a rock type provide us? When does it fail? How does it fail? To know all these parameters of rocks which are termed as physico-mechanical properties of the rocks, we do go for different types of tests. Those tests will be showing you along with equipment and what can be done with those kinds of tests. One of the primary tests that we perform is compressive strength of the rocks. In compressive strength of the rock, we go on loading a rock specimen till it fails. We also have an equipment which is much superior than the normal universal testing machines which test a rock till failure. The theory advanced and so did the experimentation. In stiff testing machines, we are in a position to continue loading the rocks even beyond its failure, and that probably is helping us to understand the behavior of the rock more. That means the post failure behavior of the rocks are also tested in this laboratory in our department, and that then defines the basic nature, or you can say DNA, of the failure of the rock types. We define and categorize rocks in terms of strain hardening, strain softening, then your very stiff rock, very soft rock, ductile rock, brittle rock. All these kinds of divisions are possible based on the post failure analysis of the rock mass, and that we are able to do through stiff testing machine of MTS company, material testing system company. Now, similarly, there are scenarios where we are not in a position to bring the rock specimen to laboratory, and therefore, we are not in a position to know the characteristic that when it will fail, how it will fail, at what stress level, at what loading will the rock fail. And because we are not knowing that, we need to know but. So, laboratory facility is not available to us. We have to work at far off places, but we need to know the quality of rock before we place ourselves or create a space in that rock mass. So, for that we get concepts of rock mass classification that helps us and is handy. People started with single parameter rock mass classification. Deere way back in 1964 came up with a concept of RQD, that is rock quality designation. It was a single parameter rock mass classification wherein as you had larger value of RQD ranging from 0 to 100. So, if a rock is 100 RQD, if rock is having a value of 100 RQD, then in that case the rock will be the strongest possible and would require minimum amount of reinforcement or support and would continue to stay safe and stable throughout its life. As we get the reduced values of RQD for any rock mass, then the quality of rock would deteriorate. Minimum of it would be at 0. So, the range of quality of rock was from 0 to 100. So, that was RQD. It was a single parameter rock mass classification which required no testing, which required no equipment to assess the quality of the rock. The process of RQD determination is a well established and documented globally and is accepted even today as a good as a concept that provides good understanding about the quality of the rock. But then people who were working, they thought that this is not sufficient condition to understand the quality of the rock. So, people started with multi-parametric classifications, rock mass classifications, depending on the needs of the structure. Like if we are going in for nuclear waste repository, then the kind of expectation for the rock surrounding the space will be totally different than that of a rock slope. Similarly, if you are in a mine, then mine has a different set of expectation from the rock mass. So, therefore, the classifications also varied. The classifications that are deployed in India do not match the classifications that are utilized in Australia or South Africa or USA, even in the case of coal mines. And therefore, it became important to utilize the rock mass classifications that were available for the sites which match the newer site. That means, if a rock mass classification has been developed in South Africa and if you want to utilize it for India, then the site must have similar characteristics in India also as was that of South Africa, where the classification was developed. So, Z.T. Binawski, then your Nick Barton came out with Q system, Binawski came out with rock mass classification system, what was called rock mass rating, RMR, and this RMR was modified in India again as geomechanics classification system of ISM and CMRI. So, that again is modifying from time to time, and now I think we should go and see various equipment and what do they test and what is the procedures of it. So, with this introduction, I welcome you to my laboratory. This laboratory is one of the most facilitated laboratory in India in terms of rock mechanics, in particularly in educational institutional setup. And even if you take any laboratory of India, then some of the facilities were created for the first time in India in this laboratory. One of that is MTS, that is a stiff testing machine. Today it costs about 4 crores, but we took it in way back in 1980, and when we installed it, we were the first to have. It is still continuing, and this equipment also has served almost thousands of samples and has determined the post failure characteristic of the different types of rocks available in India currently. Now, if you see the series of tests that this lab has been performing for different clients for academics, research, consulting and design purposes, for civil people, mining people, military people are as under. This equipment is having a competence to load up to 40 tons. These specimens can be loaded up to 40 tons, and that load is sufficient to break very strong rocks like granite basalt also. So, when we have more strong rock, we switch this to present scale where the maximum is showing 40 tons. But if suppose the rocks are not that strong, if it is medium strength, then we can change the scale, and now we will have maximum shown as 20 tons. So, same equipment will now be able to load up to 20 ton only. Now, what advantage are we getting? When we are going to have loading for softer rock, then the same scale is the space provided, minimum space that is provided gets reduced. Okay. So, we have more accurate value of failure load, and therefore, we change the scale. Suppose the rock is further soft, then we can have maximum set for 4 tons only. So, the whole scale will be showing only 4, and in the higher side the same scale will be showing 40 tons. So, 10 times of magnification is possible within the same equipment, and this is done by, as you I will give you a analogy, that as in case of car, you have first gear, second gear, third gear. So, similarly the arrangements are made within this equipment where you shift the gear to get the loading maxima of the load or levels of load 4, 20 and 40 tons. So, for softer rocks we keep it 4 ton, for harder rock we keep it 40 ton. So, same equipment is able to give us different types of loading. Even the rate of loading can be changed. So, the quantum of loading and the rate of loading and the types of loading, types of tests that are to be performed, all can be varied. Therefore, this equipment is called uniaxial testing machine or UTM. This is this machine particularly must have tested more than 1 lakh of specimen for compressive, tensile and shear for different, and must have been utilized by at least 2 to 3,000 students, and almost all the mines and civil structures in India have been tested from this, and we have about 400 to 500 specimens now, right now, lined up to be tested by this equipment. So, our lab has really contributed to nation building and input to design, and this equipment is the real workhorse of this lab. This is UTM. I told you that we will take the journey in laboratory also, where we will be going in for different types of testing that is conducted on different rock types. Now, if you see beneath the earth, you will find coal as a structure, and when you do drilling with, there are 2 types of drilling, single core barrel and double core barrel. We normally prefer double core barrel for getting cores of this type. This is a core of the coal. So, this sample is then tested in the equipment that is called universal testing machine. We call it universal testing machine. This machine is called universal testing machine because you can do compressive testing in it, you can do tensile testing in it, you can do shear testing in it, you can do single shear, double shear, and depending on the provisions that you are making, it has the capacity to provide tensile kind of stress, indirect and sometimes direct also, depending on how you are locating the specimen. So, with that we will just show you the procedure of a compressive test. I will request my colleague Shri C.B. Singh to please join me and doing this compressive testing. Recently we tested one specimen till failure for compressive strength. Compressive strength, if we want to understand, is a phenomena which tells us that up to what strength can a rock take load, or up to what stress it can take. To give a concrete example, let us say a rock can take strength, let us say Chunar sandstone has compressive strength of about 50 megapascal to 60-70 megapascal depending on its location. So, what does it actually mean? It means that when you are going to design a structure on Chunar sandstone, up to 60 megapascal of stress, it will not fail, but up to 30 megapascal, this Chunar sandstone will behave as if it is an elastic material. That means again that the moment you are loading, it is deforming, and the moment you withdraw the load, the deformation will also vanish. So, up to 30 megapascal you can consider it as an elastic material, but the moment 30 megapascal is exceeded, you will find it has started behaving as inelastic material, non-linear elastic material. Initially, earlier up to 30 it was linearly elastic, post 30 it initially behaves like non-linear elastic, and then comes a stage where it behaves like a plastic material. Some people also term a concept called acoustic fluidization. This concept of acoustic fluidization is well published in Nature, and you will find during landslides, just before the landslide, the rocks behave as if they are no more solid, but they have become fluid, they have become viscous. So, they start flowing instead of breaking. So, that kind of movement you must have watched in Kedar Ghati disaster. The whole slab of rock mass used to flow as if it is not solid, but fluid. So, that kind of conclusions can be found on the basis of just single test, that is compressive strength. And but let me make you cautious that this 60 megapascal of compressive strength that we are mentioning is for the laboratory scale. When you have to design a structure, it is field based structure. So, this 60 ton should be taken either as 12 megapascal or 6 megapascal. At the minimum, 12 megapascal at the maximum, because it is well established from the literature that compressive strength within the lab varies on, if you compare it from the field value, then the variation ranges from 5 times to 10 times. So, if a rock is giving a compressive strength of 60 megapascal in the laboratory, on field you might find that it is providing a strength of 6 megapascal or 12 megapascal. So, that kind of a scaling effect has to be utilized during design. That is important. When you compare it with tensile strength, we have a cage with which if you put a small specimen of this kind, if you put it in a tensile Brazilian cage, we say we get tensile strength. The ratio of tensile strength to compressive strength is of the order of 3 to 121. There are certain kinds of rocks which are only 3 times, means their tensile strength is 1/3 of the compressive strength. At the other end of the spectrum, there are rock types in which the tensile strength is 1/121 of the compressive strength of the rock. This property or variation in this sigma c by sigma t, or the ratio of compressive strength to tensile strength, becomes very, very significant whenever you are going to break the rock through mode of blasting, and we term it as blastability index. Just by knowing the two value, compressive strength and tensile strength, and putting them in ratio, you can understand how the rock is going to break if you are deploying blasting as a tool for breakage of rock. I have already showed you how compressive strength is done. We determine also the tensile strength. We also determine the shear strength. We also have direct shear strength apparatus with us. We determine single shear, we determine double shear, we determine post failure behavior, tensile strength, and then indirect types of compressive strength determination is also attempted through protodiacono apparatus, through impact strength, ISI method, and your point load strength index. We also utilize Schmidt hardness. Schmidt hardness is this impact method is very, very useful when we have to go to field, and my colleagues Ram Sevak and CB Singh had used it for Barn Sagar canal. On the canal we took and went with Smith hammer, because at that location even point load index was not working, and we required on-site strength characteristic. So, Smith hammer works best at that location. Similarly, we utilize need based tests are also done for P and S wave determination, primary and secondary wave velocity determination, which can be utilized for indirect determination of the compressive strength. We also determine acoustic emission characteristic within this laboratory, and we are today competent to go for triaxial strength determination of the rocks that provides us with your angle of internal friction and cohesion, which is a strong input to design of any structure inside the rock mass, that is beneath the earth surface. And we have tested rocks from Kolar to Himalayas and from Gujarat to Assam for mines and civil works also. Sometimes even concrete slabs have been brought here to get its compressive strength. So, we have a strong team of 8 to 9 people working in rock mechanics, and similarly we have range of tests and even numerical. We do not stop here. Whatever is obtained as a final concluding value of test, we then utilize it as input to numerical model, and we come out with an optimum design of structures within the rock mass. And we also do sometimes soil mechanics based testing also over here, which is utilized for waste dumps of mines, or you can say for weak rock slopes we can utilize it. We are also perceiving that there is a need of understanding the garbage dumps or solid waste dumps of municipal areas. If you see the heights of garbage dumps dumped in East Rohini, Delhi is reaching 120 meters, sometimes even more than 120 meter height. So, this 120 meter high slope requires a totally different kind of design and design inputs, and we are today prepared within this laboratory to address this issue and come out with suitable guidelines. Thank you.